Hi AP kids. We're going to try something a little different with this lecture. We're going to do a flipped lecture, and I'm going to embed a few questions that let you practice using the equations and the concepts that we're going to be learning in this lecture. So the first one for this unit is on electric fields and electric forces. So I'm going to remind you guys that there are only actually a handful of what we call the fundamental properties of matter, variables that are tied to really getting to the heart of what matter is. And the first is a variable called mass, which is represented by a lowercase m. The units of mass are a kilogram that we use in physics, and kilograms about the size of a pineapple. The second fundamental property of matter is charge, which hopefully you learned about in your freshman physics class. The variable that we use for charge is a Q, and the units of charge, the SI unit is the coulomb, but it turns out that's sort of an outrageously huge amount of charge. It's a ton of charge that would like rip this classroom apart. So more typically you see things in nanocoulombs, which are 10 to the negative 9th coulombs. There's two other fundamental properties, color and spin, but we're not going to talk about them in this class, but I just figured I'd throw them out there. Interestingly, there's a lot of similarities and a couple differences between the way that these properties influence the interactions of objects. And we'll be talking about those specifically with mass and charge in a few minutes. In this class, we're going to basically get to the level of the first level subatomic particles. So originally they thought atoms were, indivisible, but eventually we discovered we could break atoms apart into three particles. The first is the proton, and protons protons have a certain amount of mass, which is 1.67 times 10 to the negative 27th kilograms, so they're very small, obviously. And they also have a fundamental amount of charge. So the charge of a proton is given as positive 1.6 times 10 to the negative 19th coulombs. So they also have a very small amount of charge. Protons are positively charged, and these values, if you ever need them again, you can find them on your equation sheet. The other subatomic particle that we're going to be using a ton in this class is the electron, and electrons are tinier than protons, so they have a mass that is smaller. The mass of an electron is given as 9.1 times 10 to the negative 31st kilograms, so 4 orders of magnitude smaller than the proton. But interestingly, the charge of an electron is negative 1.6 times 10 to the negative 19th coulomb, which is exactly the same as the charge of a proton, except for negative. The last subatomic particle is the neutron, which we will be using, but not until the spring. Neutrons have the same mass as a proton, give or take. It's actually a little bit different, which we'll talk about later, but they are neutral and they have no charge. So scientists use these fundamental properties in our big conservation principles, which are like the guiding laws in physics. And mass and charge, by and large, are conserved. I'm going to put sort of in there because there's a few caveats. Mass, for example, can be converted into energy and vice versa, but mass and energy together are conserved. Charge is also conserved, which means that the net charge of the universe is staying the same. We actually can create and destroy charged particles as well, but whenever we create a proton, for example, we also create an electron so that we keep the net charge of the universe the same. Now, it turns out that the net charge of the universe is essentially zero, or very, very close to zero, which is, it seems, a massive coincidence because there's nobody that's been able to show why it had to be zero. However, if it was not zero, life as we know it wouldn't be possible. So that's kind of an interesting side note as it comes down to charge. You'll hear the word point charge a lot in this unit, and a point charge is a system of subatomic particles, so protons, electrons, and maybe neutrons if you want to. And we assume that for the purposes of this class, it doesn't take up any space. It's tiny. You can always find the mass, the net mass, or the total mass, or the total charge of a point charge by just adding up the fundamental properties, masses, and charges of the subatomic particles that are part of it. So for example, here is a point charge. I'm calling it point charge number 1, and it has 6 times 10 to the 15th protons and 9 times 10 to the negative, or 10 to the 15th electrons. If I wanted to know the mass of point charge 1, I'm just going to add up all those masses. If I wanted to know the charge of point charge 1, I'm going to add up the charges of all of the protons and electrons, which you can make a shortcut for that just by subtracting, just finding the difference. Since one proton cancels out one electron, we could find the total charge of this just by doing the charge of the net leftover electrons, which would be 3 times 10 to the 15th. So this is the first embedded practice problem that I'm going to put in this video. I hope that you will stop and take the time to solve it, because I think that these skills of these little problems are really going to help you when it comes to solving more complicated ones, but it's up to you. So the problem is, if you have a point charge that I mentioned before, go ahead and actually solve for the mass of point charge number 1, and also find the charge of point charge number 1. If you don't feel like doing these problems, you can always just put in whatever random number and move forward, but I hope you will actually try to solve them, and I'll have solutions in the videos as well. So we care about the particles individually, but one of the reasons they're so interesting is because of the way they interact with each other. And those particles interact through things called force fields. And I think I previewed this in the beginning of the year about gravity a little bit, but force fields are essentially how point charges communicate the magnitude and size and the sign of their fundamental properties to each other. I like to think of them as sort of like, you know, a perfume or a smell that is coming off the point charge that tells, you know, spreads through the space around it, and if there's another point charge somewhere nearby, it can smell that smell and learn something about the point charge that's kind of spreading that smell. Mathematically, we model these things as vector fields. So vectors are shown graphically as arrows, and they technically extend forever. So the force field coming off of a point charge goes through all space. So I've drawn, for example, a vector field that represents the gravitational field of point charge 1. I mentioned this earlier. You've learned as little g as the gravitational acceleration, but I prefer to talk about it as the strength of Earth's gravitational force field. In any case, that gravitational field has a direction. It is towards the object that's exerting it, because it's a gravitational field. And the arrows, the number of the arrows, or the density of the arrows, or the length, or, you know, kind of boldness of the arrows, is one way to represent the strength of this gravitational field. And I've drawn it as relatively weak because there's only a few arrows and they're not very long. Point charge 1, besides having mass, also has a net charge. And so that charge is going to cause point charge 1 to have a second force field exuding from itself, and that will be the electric field. So the electric force field is represented by the letter capital E, and you'll notice that I've drawn that E as a much stronger force field than the gravitational force field. There's a lot more arrows, they're longer, and they're also bolder. The direction of E we'll talk about more later on, but in this case we knew that point charge 1 was a negative charge, and you'll see that I've drawn the direction of E as towards that point charge, which is mathematically accurate. If the point charge was a positive charge, we would flip the direction of those arrows and they'd be pointing away. So there are many similarities between G and E, which is really helpful for you guys in coming up with kind of a model for what electrical fields do, because they act just like gravitational fields with a couple small differences. So for example, both of these force fields depend on similar things. They both depend on the fundamental properties of the object. So in gravitational force fields, that's mass. In electric force fields, that's the charge. And both of the strengths of these force fields have linear relationships with these fundamental properties. They also depend on the distance from the object. So the closer you are to the object, if you're right here in this location near the point charge, the gravitational force field is stronger, and also the electric field is stronger. If you move further away from that point charge, like for example over here, both of those force fields get weaker by the same ratio. It's an inverse squared relationship between the distance from the object and the strength of the force field. And then the third thing that's going to be in the equations, when we actually come up with that in a second, is some sort of universal constant. So these are just things that we've experimentally determined so that we can accurately represent the strength of these force fields and the impact that they have in surrounding objects. In gravitation, that universal constant was G. We called it the universal gravitational constant. For the electric force field, the universal constant is a lowercase k, and it's known as Coulomb's constant. So, given those three relationships, the equations have this identical form. Gravitation is little g is equal to big G times the mass of the object causing it divided by the distance squared. And there, again, is the value for that gravitational constant, 6.6 times 10 to the negative 11th Newton meter squares per kilogram squared. The new equation for the electrical field strength looks exactly the same with slightly different variables. So E, electrical field strength, is equal to K times Q, which is the charge of the point charge, divided by distance squared. And Coulomb's constant is equal to 9 times 10 to the 9th Newton meter squared per Coulomb squared. There are a couple differences between these force fields. One I've already mentioned, and that is that G is always attractive, which means the arrows are always going to be pointing towards the point charge or point object, point mass sometimes, whereas E can attract or repel, and the direction of the arrows is going to represent which direction E is pointing. We are always, by convention, drawing E towards negative objects and away from positive objects, as I've shown in the drawing to the left. And the other main difference that often gets tested is that G is way, way weaker than E for any object, pretty much in the universe. And you can even see this when you look at those equations. Look at the constants, right? So for gravitation, you have to have a huge mass because the gravitational constant is such a tiny number to get any kind of reasonably strong force field. Whereas for the electric force field, it's a huge constant, so even a small amount of charge causes a relatively strong electrical force field. So given that G is way, way weaker than E, how come G is something we witness in our lives every day when we drop objects and they fall, and E is not? Well, the answer is because of conservation of charge. We know that there's basically the same number of protons and electrons in this universe. So in general, most objects have the electric field canceled out because we have a proton in the object exerting an electric field in one direction and an electron exerting an electric field in the other direction. So at any point in space, if you have multiple force fields acting on an object of the same type of force fields, G can't cancel out an E and vice versa, but if you have an electric force field to the right and an identical electric force field to the left at some point in space, then your net electric force field would be 0. So in all of these vector field problems, you can find the total value of that force field by adding together the sizes and the directions of the force fields that make it up. So this is the second space where I'd ask you to do a practice problem to sort of improve your skills at this. This is sort of not a common one on the test just because it requires a little bit of trigonometry and they don't want to usually make you take the time to do that, but it would be good practice to make sure you're up to speeds on your vector addition. So I've got 2 point charges on a XY axis. Point charge 1, which is this purple one here, has magnitude negative 4.8 times 10 to the negative 14th, or sorry, 10 to the negative 4th coulombs, and it's located at 0, 0.1 meters, so 1 meter up on the y-axis. A second point charge, magnitude 7 times 10 to the negative fourth, so slightly larger point charge, is located at 0.2 meters on the x-axis and 0 on the y-axis. So the question is, what is the strength and direction of the electric field located at the origin? So if you went to the origin, what kind of electric field would you be experiencing? How big is it, and in what direction? So take a few minutes and solve this problem before you move on. Thanks. The last chunk of this lecture is going to be on a new variable called the electric force, and it's represented by a capital F with a lowercase e next to it. It's a force, so it's going to be measured in newtons, just like every other force that we've ever had in this class. I'm going to remind you that Newton's third law says that all forces are actually equal and opposite interactions between two objects. So for an electric force to exist, you actually have to have two objects. Now this is not true for the electric field, right? You just need one point objects for an electric field, and that electric field goes everywhere in space. You don't have to have another object to have an electric field. However, to have forces, you actually have to have two objects. So I've drawn down here an object with a charge. It's a single proton, and I've drawn an electric field in the space around that thing. So where are the two objects? Well, one of them's a proton, and the other one's off the screen somewhere. We can't see it, but we know it exists because that electric field had to come from somewhere. And it didn't come from the proton, right? The electric field from the proton itself would look something really different. In general, well, not in general, as a rule, objects can't respond to their own force fields. So like, the Earth is not attracted to itself with gravity. The Earth attracts other objects, and the same is true for electric force fields. So proton is emitting an electric force field, but it's not attracted to itself. So there would be no force if there was just one object. Sometimes we label our two objects the source and the test, and I'm going to be doing that frequently to help you see in an equation which object a variable is related to, and this sort of helps you keep track of them. And the source is often whatever object is kind of off the screen. So I would say this is an E field from the source object. And in this case, the proton is obviously the object of interest. We'll call that our test charge. Occasionally you get a problem that just mentions a test charge and doesn't say any information about it, like it doesn't say what the charge is or how many protons or electrons it is. It just talks about a generic test charge. In that case, the test charge is always assumed to be a lone proton, which is why I used it in this problem. So the generic test charge is always a lone proton. So the force on a test charge is going to depend on how strong the strength of the electric field is at that location, right? So this test charge is going to experience a force from the source object, and the stronger the force field is, the bigger that force is going to be. It's a linear relationship. And it also depends on the charge of the test charge itself. So that proton is a really tiny, tiny test charge, but if it had, 2 protons, for example, it's going to experience more electric force than if it just had 1. So there's a linear relationship between the amount of charge on the test charge and the amount of force it experiences. Those are the only 2 relationships in the equation for Fe, so it's a pretty straightforward equation. I've added those subscripts. They're actually probably not on your equation sheet, but would be useful to think about. So the electric force is equal to the electric field from a source object times the charge of the test object. And I want to put those subscripts in there because I want you to realize that there are 2 objects involved, right? Every force is an interaction between 2 objects. These have to be different objects. They can't be the same object, or we have no electric force. So if we go back and take the equation we derived a couple slides back for E and plug it back in, we end up with another equation that is known as Coulomb's law. So it's the same equation, it's the last 2 equations combined basically. Fe is equal to K, which is the Coulomb's constant, times the charge of the source times the charge of the test, divided by the distance between them squared. This form is another useful form to see this equation in, because we can see the two objects again. We can see that we have a source charge and a test charge. And I also really like this because it helps you see the Newton's third law relation. We know that, multiplication is commutative, so it doesn't matter what order we multiply these things, and it doesn't matter which object's the source and which object's the test. You're going to get the same amount of force either way, which is Newton's third law. Just as by the way, as an aside, remember that equation you used all the time in AP Physics 1 and maybe even in freshman physics, which is, the weight of an object, the force of gravity, is equal to 10 times the mass of the object? Well, that equation is actually the identical form as this new equation for the electric force. The force of gravity is equal to the gravitational field of the source, which is Earth, right? And that's our 10. We know that Earth pulls downwards with 10 newtons per kilogram of force, times the mass of the test object, which is anything on Earth that I care about finding the weight of. And if you again take the equation for little g and plug it back in, we get that universal law of gravitation, which is that the force of gravity is equal to gravitational constant times the two masses, the source mass, which is likely Earth, but not always, and then the test mass that you're interested in divided by the distance between them. So again, the parallels between gravitation and the electric force should jump out at you and should hopefully make this unit kind of come into context a little bit more. So this is the last slide in the slideshow, and it's a big, crazy practice problem that really pulls in all of the concepts from before. So let's assume that that electric field I've drawn on the paper has a strength of 21,000 newtons per coulomb at the location of the proton. The first question is, how much force would that proton be feeling at this moment, and in what direction? The second problem is, what would be the acceleration of the proton at that instant? The third problem is, if the object that's the source of the this external electric field is 2 meters to the left of the proton, how big is the charge of this source, and what sign is it? Is it positive or negative? The next question is, what is the size and direction of the electric force that the source object is feeling from the test proton? So flip this question and ask about the force on the source object. And then E is, if you replace the proton with an electron, would this new electron feel more or less or the same amount of force compared to what the proton is feeling? And then the last question is, would this electron experience more or less or the same acceleration of the proton as the proton? If you got through this whole slideshow and also did all the problems, give yourself a pat in the back. You're really doing everything that you can do to make sure that you have a successful unit. Thank you.